Welcome back. We're going to look now at this notion of variadic function, but in a C++ context. And this is interesting. It's a nice adaptation of the notion, but it brings a lot more to the table. It's quite a bit more powerful. So what I'm introducing now is known as variadic templates rather than variadic function, which means now that the variable number of arguments is not for the functions, it is for the template itself. So what we're doing is actually introducing support for types at compile time through a variadic number of templated arguments. So this is a compile time feature, which means all of a sudden, unlike in C, we restore the ability to check whether the program and the calls to a variadic template make sense at compile time. We don't have to wait until we run and find out that there is a problem or have all sorts of ugly crashes because we have a mismatch between the number of things passed and the number of things the function is expecting, or between the types of the thing passed and the types that the callee is expecting. All of these kinds of errors can now be called at compile time, right? So this is nice. I can catch all sorts of problems at compile time rather than runtime. And that is the big improvement over this. Now, at its core, the idea is to use a templated class or a templated function with a variable number of template arguments. So all the action is happening in the template declaration, not so much in the function declaration. And everything will be handled at compile time, which is really nice. And that shows you that this is a natural follow-up to the topic of metaprogramming that we covered last time and that we approached as a way to do computation at compile time. It is also metaprogramming here. We are also going to exploit the ability of the compiler to create families of functions that can carry out the computation we wish to see. And that is why this is all about metaprogramming. Now, fundamentally, again, we have 3 points of view. Just like in the C case with variadic functions, where we had usage, declaration, and implementation, in the C++ case, we're going to find usage, declaration, and implementation. We have all 3 aspects as well. And I'm going to start with the 2 easy ones, which are usage and declaration. And in the next videos, we're going to explore how to implement variadic templates. First thing first, the syntactic elements are very similar to those in C. It's a reuse of this idea of using an ellipsis. When I'm going to define a template parameter pack, so that's the same idea, I have a parameter pack, but when I'm going to declare it, I'm going to have an ellipsis in my template declaration. So it won't be in the prototype of the function, it will be in the template clause that is shown prior to the object we're defining. And that template definition, that parameter pack, can actually be instantiated with 0 or more types. I could have actually an empty list of additional types. That's all fair and square. I can actually do that. And I can use, unlike in C, any type I want. I can use integers, I can use float, I can use doubles. There will be no funny conversion business going on. It's all very, very clean. So how is it done? Well, let me show you an example with a type that's coming here that we're doing ourselves, but is reminiscent of a type that exists in the STL, which, of course, you imagine they're using variadic template to build it. Here, I'm rebuilding for you the notion of a tuple. So remember, a tuple is a group of 0, 1, 2, 3, or more attributes that can have different types, and I basically want to see them as a bundle in a sense, right? So the way a tuple is defined, I'm not showing you the guts of the implementation. It's empty here. I just want to show you the declaration. I have a template, then follows my usual class, and normally you would see a type here. What I'm going to do is not give you a type. After the keyword class, or type name, you can use type name as well, of course. After the keyword class, I'm using an ellipsis, ... which basically means, oh, by the way, this is a parameter pack. And that parameter pack will have a variable number of types, right? Now we're talking about types and not arguments. And I'm saying, giving you the name of the parameter pack. So types Note that I wrote it as a plural to remember that this denotes a parameter pack containing multiple types. After my template stanza, I give you my usual type. So this is a struct tuple, and of course I put an empty implementation here. That's not the important part. What matters is that I'm going to actually show you how we use this. So I want just to show you the declaration, not the implementation, and show the usage pattern, which you see here. I define 4 different tuples in this code. The first one, T0, is a tuple, and I'm using the 2-angle bracket back to back, meaning the parameter pack is empty. There are no parameters inside this pack. The second one is a traditional pair of integers. It's a tuple, and there are 2 types in here, int and int, so T2 is a pair of integers. And that's all I care about here. This is the declaration of the types. And of course, naturally, I would expect to find in my implementation of tuple methods to retrieve the first and the second of the pair and whatnot. But this is not the interesting part. I'm just focusing now on, remember, declaration and usage. So we've seen how to declare, and we see 2 usage scenarios here. The third one is giving us a triplet, and the triplet has an int, a float, and a character. Completely okay. The fourth one is the most complex up to this point. It is also a triplet. It has an int, a string, which is an object. So you don't have to use just scalars. You can use C++ objects as types inside your parameter pack. And the third thing is another parameter pack. It's another tuple. So I can nest tuple. I can have here a structure which is quite simple. My structure will have an int, a string, and then the third thing is going to be a pair, int. Oh, I should actually line this up properly. So let's me move a little bit to the side and change color so that this works a bit better. So I have an int, a string, and then I have a pair of int. Notice that this is completely okay. This is a parameter pack with 1, 2, and 3 types. The third type is itself a parameter pack with 1, 2 types. The second one was an object, the first was a scalar. Completely okay. I can mix and match as I build my parameter pack. It's quite straightforward. So that's all there is about declaration and usage. It's quite straightforward from an end user standpoint. You probably already have used such variadic templates without even realizing. And I say probably, I should actually say certainly, because you have made use of something that you come to love and know under the name of shared PTR. And a shared PTR is implemented, you guessed it, with variadic templates. So we're going to eventually look at that, but in the next video, I'm moving over to see how do we implement a function that is based on a variadic template. And to do that, we're going to rebuild printf, but now it will be type safe. It will be a type safe version of printf that knows all the type at compile time, even though we are not going to actually see anything until we see the call, right? So that's the beauty of it. For that, see you next time.